Okay, so last time we introduced the R transform in an analytic way, and today we want to see, really application, how we can use it to calculate. So let me just recall we did. So we have the Cauchy transform. So we want to calculate, of course, the Cauchy transform or probability measure, because from the Cauchy transform you can get the probability measure by the Stieltjes conversion formula. Okay, but if we're dealing with free convolution, the Cauchy transform is not so clear how it behaves with respect to free convolution. So we go over to the R transform. And the R transform, in the beginning we defined it as generating functions, essentially the free cumulants. But now we took a more analytic point of view. And from this, the main point is that the Cauchy transform and the R transform satisfy a relation. Namely that the R transform is 1 over Z is the inverse of the Cauchy transform. Okay, that's something which we observed in the beginning, but last time we took this as our point of departure by saying we want to define the R transform by this equation. The Cauchy transform is given, and so then we saw that in some suitably chosen domain, we can define R transform, and there's a unique one which satisfies this equation. Okay. And then if we have the R transform, then the free convolution is easy because the R transform is additive. Okay. And then of course we can go back again by this equation to Cauchy transform. Okay, and that's what we want to do today in some examples to see that really we can use this to calculate something. So let us do example. Maybe somehow the simplest example, which maybe a priori is not so clear. Free convolution is a quite non-linear operation, and it's not really clear what the result of any free convolution is. The only free convolution which we can more or less get directly from the definition is the convolution with a delta function, because this is just a shift of the other measure by the amount of the delta function. Okay, but any other thing is not so clear what you get, and the simplest situation which we want to consider is the convolution of a Bernoulli with itself. Okay, so I take the convolution of two measures, but actually the measures are the same, and both of them are the delta Bernoulli, which is the probability measure with masses 1/2 at plus and minus 1. Okay, so we want to know what is the convolution of this guy in itself. So we are looking, so I have Bernoulli, which has mass 1/2 plus and minus 1, and we want to convolve this with itself. Minus 1 plus 1. And the question is, what is this? And from the definition, this is not directly clear. The corresponding classical problem, of course, is trivial. That's very easy. But here, it is not easy. The result is not clear and maybe it will be unexpected, but we get there. But so let's see whether we can calculate this. Okay, so what do we have to do? We have to calculate the R transforms of those guys. Because of the level of the R transform, we know what is going on. For getting the R transform, we start from the Cauchy transform. So we calculate the Cauchy transform of mu. This is the definition, the integral 1 over z minus t, integrated with respect to mu t. Mu is now a discrete measure, so it puts mass 1/2 at minus 1 and plus 1, so this is nothing else than a sum over choosing t equal to plus 1 and minus 1 with mass 1/2. So this is 1/2, and I have 1 over z. Then I have t equal to minus 1, so plus 1, and I have t equal to minus 1. So that's a Cauchy transform. And of course we can calculate this. So this, of course, is this times this, which is z squared minus 1. And then I have to multiply here with z minus 1 and here with z plus 1. The plus and minus 1 go away, and I'm left with 2z, which cancels this 2 here. So I just have this z. So the Cauchy transform of this is very easy. Good. Okay, but we have to go over to the R transform, and the R transform is defined by this equation. So we have to look first whether we can do this. And maybe usually we call this R plus 1 over Z, we call this K. So maybe, let us first maybe calculate K and then subtract the 1 over Z. Okay, so K mu is given as the solution of, okay, so K is the inverse of the Cauchy transform. So this means if I'm plugging in G as an argument K, so I have here the Cauchy transform of mu, I take here the K transform of mu, then this is the inverse. Okay, so that's the equation for K, and I mean we have an explicit form for G now, so I can just plug this in. So what I have here is now the argument divided by argument squared minus 1. The argument is now K mu of Z, and divide this K mu of Z squared minus 1. Okay, so you see Z is equal to this, and this gives me an equation for K. Of course, a quadratic equation which we can solve for. So our equation is what? Of course, I multiply with this, I bring this on the other side, and then I also divide by Z, so I have K mu Z squared minus, bring this on the other side, K mu of Z divided by Z, and I'm left with this one here. This is I get this minus Z here, bring it on the other side and divide by Z. Okay, so this is my quadratic equation, and quadratic equations we can solve. This has a solution. This actually has two solutions, but we have to choose the right one. I mean, we know the R transform is a mapping which maps 0 to 0. And of course, there's only one solution of this, which has this property. And that's the one which we know. So what we saw last time, I mean, we have a unique solution of this equation, but of course, I mean, this is a solution which maps the neighborhood of 0 to the neighborhood of 0. Okay, so I mean, there's another solution which maps somewhere else, which maps 0 somewhere else, but that's not the one in which we're interested. So what we get is this K mu of Z is 1, and maybe let me write it down a priori. Both solutions, 1 plus 4Z squared, square root of this, divided by 2 times Z. So that's the general of this, and then of course the R transform, we know what the R transform is doing. So the R transform is given by subtracting 1 over Z. K is R plus 1 over Z. So we get for the R transform we have that R of Z. So this is K function, and then we are subtracting the pole at infinity, so 1 over Z, the pole at 0. And of course, what is this? This is now, you see, we have here 1 over 2Z, we are subtracting 1 over Z, so we get minus 1 over 2Z. So we still have this square root, we have plus minus 1 plus 4Z squared, and then we have minus 1 divided by 2Z. So here's just the square root, and this 1 over 2Z minus 1 over Z is minus 1 over 2Z. Good. Okay, so we have two solutions, but only one of them has the property that at 0 it is 0. Okay, and so for this we need the plus sign, because then this here essentially behaves like 2Z, and then we have 1 minus 1. So since 0 has to be 0, we know that our solution is the one with the plus sign. So of Z is equal to 1 plus 4Z squared, square root of this, minus 1 divided by 2z. Okay, so very nice, simple, okay, so square root. Okay, so that's our starting point. Now we know the R transform of mu, and now we want to calculate the reconvolution of mu with itself, which means we should add the two R transforms, because they are the same, because our measure is the same. We just multiply the R transform with 2. So the level of the R transform, the free convolution of something with itself, is just a very linear thing, multiplying it with this 2. Now, of course, the point is that if you go back to the Cauchy transform, the relation between the Cauchy transform and the R transform is nonlinear. And it's not clear what the effect of multiplying with 2 on the level of the R transform, what this really means for the Cauchy transform. Okay, but so let us do it. Here we can calculate everything. Okay, so now we go over mu plus mu, the free convolution, and then the corresponding R and Cauchy transform I just denote by R and G. I'm not putting Ax there. So the R transform to measure mu plus mu, that's the measure which we want. So I just call this R, and in the same way the Cauchy transform. Mu plus mu, I just call G. And that's really the thing which I want. Because from there I can get the measure by the Stieltjes inversion formula. Good, okay, so what we can calculate very easily is the R transform of mu plus mu. We have R of z, so this is just the R transform of mu of z plus the R transform of mu of z. So this is mu plus mu, and we know the R transforms are additive for the free convolution, but because they are the same, this is just 2 times the R transform of mu of z. Okay, and you see, multiplied by 2 is very nice for this case, because it just cancels this 2 here. And then if you go to k, you see that we have a 1 over z, so even this gets cancelled. So it's getting very nice in this case. Okay, so this here is this one, but multiplied by 2, so it's 1 plus 4 z squared, square root, minus 1 divided by 7. Okay, then we should go back to the Cauchy transform by this equation again, and the argument there is R plus 1 over z, which we call k, so I should also add 1 over z to this one, and you see I have here minus 1 over z. So adding 1 over z to this is really gives very nice, because it just cancels this one. So we see the R transform in this case is getting simpler than the one here. Good. Okay, so K of z, which is R of z plus 1 over z, is now just we just remain with this term. So minus 1 is getting cancelled by this 1 over z. So we have 1 plus 4 z squared divided by z. Good, so that's the R transform of mu plus mu, and now we have to go back to the Cauchy transform. What we need is the Cauchy transform, and so again we have to use this relation between the Cauchy transform and the R transform, and now it's better to use the other way. I mean it says that R plus 1 over z is the inverse of G, so we can write it as saying that G of k is equal to z, but it's also the other way around, that k of g is equal to z. Here we knew G, so it was good to use this one. Now we know R, and so it's better to use the other one. So from this we get that G is determined by, okay, now I take the equation that if I plug G as an argument to k, I get back z. K or G of z is equal to z. It's also saying that G and k are inverse with respect to composition. Okay, now because I know k, this gives me an equation for G. So then this k was this, so it's 1 plus 4 times the square of the argument, but the argument is G, so I have G of z squared, the square root of this, divided by the argument, which is G of z. So again, we have the equation z is equal to this divided by this, and this is again a quadratic equation. So then I just square everything, and then the square root goes away. I get z squared times g of z squared is equal to what I have here under the square. So this tells me that z squared times g of z squared is equal to 1 plus 4 gz squared. I just square the equation and bring the g of z to the other side. Of course, I bring it to the other side and then I square the equation. Good. Okay, and now you see that actually this is a quadratic equation which is very easy to solve because there's no linear term in g. So actually, this is to bring this on the other side, and then I have g of z squared, and I have z squared minus 4 is equal to 1. And then I'm just dividing by z squared minus 4 and taking this to the square root. So what I get is g of z is equal to 1 over z squared minus 4. Good. And you see, I mean, this looks very different from the g from which we started. So, I mean, the effect, I mean, on the level of the R transform, the effect of doing the free convolution is just multiplying by 2. Not much has changed there. But if I go back to the Cauchy transform, then the effect is going from this to this. Okay. And I mean, this here is just a rational thing, but here I have square roots. So this means this is maybe a quite different object than from the ones from where I started. Good, but we can calculate the corresponding distribution because we have the Stieltjes inversion formula. Right? I mean, we have explicit formula for G, and then we can use the Stieltjes inversion formula for getting explicit formula for our distribution. Okay. But maybe first of all, we should think a little bit what we have done. Of course, we have solved here those equations, and this equation is of course only an equation which is true in the neighborhood of infinity. Because what we did last time, I mean, we really looked on the neighborhood of infinity and the neighborhood of 0, and the Cauchy transform goes from a neighborhood of 0 to a neighborhood of infinity, and the R transform goes from 0 to 0. So all the equations which we have are only valid for z sufficiently small or sufficiently large. This means the solution which we got here is actually only valid for z sufficiently large, in the neighborhood of infinity. Okay, but of course, what we want is the Cauchy transform close to the real axis. I mean, knowing it at infinity doesn't really help us so much for getting the distribution of our measure. Still, this inversion formula tells us we have to go to the real axis. And of course, this means that having the Cauchy transform at infinity, which is more or less saying we know the power series expansion about infinity. This is not really so helpful. We really need an analytic formula close to the real axis. But the Cauchy transform, we know, the Cauchy transform is an analytic function in all of the upper half plane. And so if I have a formula for it, which gives me an analytic function, and this formula makes sense as an analytic function in all of the upper half plane, then I know by properties of analytic functions that they must be the same. Because if I have two analytic functions which agree on some set, on some dense or whatever set, then they agree everywhere where they are defined. Okay, so this means this formula, which a priori derived only in the neighborhood of infinity, is also valid everywhere, just by analytic continuation. Good. Maybe I wrote this now. I mean, this is an important point, and this is really why we use analytic tools. I mean, if we could do the same thing as calculation, we could say this is just consider this just as a formal power series. But then this would only be something which would give us information about the coefficients, which is the expansion about infinity. But for the Stieltjes inversion formula, we really need something analytic. Okay. Good. So note that by theorem from last time, we know this form, G only if Z is large, if we are in the neighborhood of infinity. But on the other hand, we know that the Cauchy transform is an analytic function everywhere on C++. But since G analytic on C++, this explicit form can be extended from this neighborhood of infinity to all of C++. Of course, using some effect that we use here a branch of the square root, which defines this as an analytic function all of the upper half plane. Also, one has to think a little bit about which branch of the square root am I using. But I mean, I don't want to go into this, but I mean, because we're using in such a way that this expression here is an analytic function of the upper half plane. Okay, and so this means that we really have now this formula of all of C++, and we can use it for the Stieltjes inversion formula. So hence, we can also use it if we go with our set to the real axis, as is required by the Stieltjes inversion formula. Plus form of the free convolution of μ plus μ by the Stieltjes inversion formula, which is inversion formula. Okay, so let us see what we get there. Yeah, I think I can erase this here. Okay, so what does the Stieltjes inversion formula tell us? I mean, it tells us essentially that we should take the imaginary part of the Cauchy transform at the point where we are interested, but going a bit into the complex plane, and then at the end letting this small imaginary part go into circle. So essentially it tells us that the μ plus μ, let's say, relative at the point t. If this would have a density, then we would get the density by having -1/pi, and then we take the limit epsilon going to 0. We take the imaginary part of our Cauchy transform, for which we have an explicit formula, so it's 1/, and then we take the Cauchy transform at the point t, going a little bit in the upper half plane, so the I epsilon. And so it's z squared minus 4 square root of this. And going with epsilon to 0. Good. Okay, and when if you're choosing nice form of the square root, then actually this is continuous, and then you can just go let epsilon go to 0, and essentially get the same formula. So what we have here is -1/pi. I have the imaginary part of 1/t² minus 4. Okay, so you see, in order to get something, we need here an imaginary part. And of course, if t² is bigger than 4, then here I have something real, so I get here just the ordinary real square root, which is a real number which does not have an imaginary part. Okay. So this means outside the interval from -2 to +2, this quantity is 0. But if I'm inside this interval, I have here t² minus 4, which is negative, And then of course I get I times the other way around, or the square root is then has imaginary part, and the imaginary part is I times, and I have the square root of 4 minus t squared. And because I'm dividing, the I gives a minus I, which goes away with this minus, which is good. I mean, the density should be positive. No? I mean, a priori, it looks as if you would have a negative density, but of course, there must be another minus coming somewhere from here. And that's what happens here. No? So what we get is really, we get 1 over pi, and we get here the square root of t squared minus 4, if t is between minus 2 and plus 2. And otherwise we get 0. So we get, of course, something which lives on a compact interval, because we have to, of course, the free convolution of a compactly supported probability measure with itself, we get a compactly supported probability measure. Good. Okay. So so you see somehow maybe the strange thing that we really get density here. We started from something which had 2 atoms, no density. We take the free convolution of this with itself, and then what we get is something which has density and no atoms. I mean, you really can calculate that this is a probability measure. So you see 1 over pi really is exactly what we need. This is really a density of a probability measure. If you integrate this from minus 2 to plus 2, you get 1. Okay, and so what we have here is actually the density of a probability measure, which is also well known from classical probability theory, and it's called the arc-sine distribution. And why arc-sine? Because if you integrate this, then it's the arc-sine. Okay, so the distribution function of this is the arc-sine. So what we get is the mu plus mu is a probability distribution which has this density, and this is what is called an arc-sine distribution. The arc-sine distribution. Okay, so this means in this picture there, so we know what the result is, but the result actually is something maybe unexpected. Okay, so it lives from minus 2 to plus 2, that's maybe also unexpected, but there it has a density. And then, of course, this density here goes to infinity if we go to plus and minus 2. So this really looks somehow like something like this. Okay, so here it goes to infinity, but there's no atom. So it's really a continuous density. Good. Okay, and this shows us that free convolution behaves maybe in strange ways compared to the classical convolution. And of course, this here, so we're also going to call mu to the power 2, with respect to the additive convolution. Also, we're taking 2 times this measure of convolution is itself. Good, so let us make a few remarks. We see a few maybe strange things here compared to the classical one. In principle, the arc transform is somehow like the Fourier transform machinery for classical convolution, but the outcome, what you really get in concrete examples, is maybe quite different from things happening in the classical world. So let me make a few remarks on this. First, of course, is that if we take the convolution of discrete measures, we can get a non-discrete measure, which has no atoms, but just a continuous one. And of course, this does not happen in classical world. Corresponding to the side. In classical world, of course, is very different. It's just a measure which has 3 atoms. And which is easy to calculate. Of course, for doing a classical case, you don't need to Fourier transform machinery, you just do it directly. But here we don't really have a direct way of calculating the free convolution. Good. Okay, so let me make those remarks. So it's this general idea that in free probability theory goes on a high level parallel to classical probability theory, but there are many details and things which are really different and surprising if you compare. So free probability theory is not just a bijection of a classical world where all results in the classical world are translated into the same kind of results in the free world. I mean, the general idea is translated, but the outcome sometimes is quite different. Okay, so here are some remarks. So the first remark is that that free convolution and classical convolution in concrete situations can be very different. This shows free convolution behaves quite different from classical convolution. For example, so what we see here in this case, it can happen that if I take the free convolution of a discrete measure with another discrete measure, as I did in this case, so this can be continuous. So atoms disappear. And of course, in the classical case, this does not happen. In the classical case, take the classical convolution of two discrete measures, I get again a discrete one. This side is also discrete. And for example, of course, in this case, you have to take the classical convolution of Bernoulli, depending on plus and minus 1 with itself. And it's clear what we get. I'm just adding two random variables, taking on the values plus minus 1 is probability 1/2, and they are independent. And then, of course, the possibilities which I get is minus 2, 0, and plus 2. And of course, minus 2 can only happen if both are minus 1, which happens with probability 1/4. Then 0 can happen if one of them is minus 1 and the other is plus 1, which happens, there are two possibilities for this, with probability 1/4, so this actually happens with probability 1/2, then the 0, and of course, can also happen that I get a 2 if both of them are equal to 1. Okay, so you see, I get here, again, a discrete one. And also, of course, it's very easy to calculate this, but actually, this calculation you can also see as a distributivity of this operation here with this plus sign. So actually, classical convolution in a sense is linear, but is distributive. And this means, it's very easy to calculate any classical convolution of discrete measures. Classical case is, at least for these discrete examples, it's easy to calculate. Since this classical convolution is distributive. So it really behaves like a multiplication here, which is distributive with respect to this convex combination of my probability measures. So this means, this result I can also just get formally by saying, okay, I want to do delta minus 1 plus 1/2 delta plus 1. I take the free convolution, this is itself, plus 1 plus 1. And I just do this by multiplying it out and then take the free convolutions of this with this and this with this and so on. I'm just multiplying the weights. So what I get is, I always have 1/2 times 1/2, so I always get 1/4, and then I have delta minus 1 minus 1 plus delta minus 1 is delta plus 1 plus delta 1 plus 1 is delta minus 1 plus delta minus 1 is delta minus 1. And of course now I'm getting exactly the four possibilities which are counted here. I mean the convolution of delta functions, of course, is also something which is clear. No? So this is delta minus 2, this is delta 0, this is delta at 0, and this is delta here, twice the plus delta at 2. Alright, so you see, we get this result just by formally using distributivity of these convex combinations and then using that convolution of two delta functions. This is very easy. No? The delta function A and the delta function of B. The convolution of this is the delta function A plus B. Good. And of course, for the free convolution, we still have this delta property. No? The free convolution of a delta function at A and a delta function at B is the delta function of A plus B. But this tells us then that for the free convolution, we don't have this kind of distributivity. Because if we would have it, then we must get the same result here, but we get a very different result. So this tells us that the delta function is not distributive, and we can not reduce the free convolution of the convex combination of delta peaks to our knowledge of what happens with the delta peaks themselves. In the classical case, you can do this. This means the free convolution is not distributive, which is very different. Which means essentially it's a kind of non-linear operation. This distributivity tells us the equations governing the classical convolution are kind of linear. And here we have a very non-linear operation. In particular, this relation between R and G. That's very non-linear. Good. Okay. So since we still have that on a level just of delta distribution, so delta A, free convolution is delta B, that's the same as in classical world. No? So that's delta of A plus B. But then this tells us that this free convolution cannot be distributive. No? Because otherwise we could calculate in the same way for the sign. We know it's not true. Also, this shows free convolution is not distributive. In another way, I mean, it's kind of non-linear operation. Free convolution is a non-linear operation. It's linear on the level of the R transform, but the relation between G and R is non-linear. Linear the level of the R transform. Relation between G and R is non-linear. Good. Okay. And so there's even maybe more striking differences between classical and free convolution. And for this to see maybe something like this, let me generalize this example to taking higher powers. So here we consider the free convolution of mu with itself. So essentially we took the second additive convolution power of mu. But of course we could also take the convolution of this guy 3 times or 4 times with itself. So we could consider mu to the power n. In principle we can do a similar calculation. So let me just do this and then check whether we see anything interesting here. So second part of the remark, let us generalize the example which we just did. So example 13. mu to the plus power 2, but to the general one, which by definition just means that I'm taking the n-fold free convolution of mu with itself. Oh. So I'm taking here n times n, the factor and convolving it with itself. And of course we can do the same, because we just have to take the R transform of mu, and then instead of multiplying it with 2, we multiply it with n. And then of course we have to go back and see what the Cauchy transform gives us. Okay, so let me indicate the main steps. I'm not doing the full calculation, I just show you the main steps. So we have 4. So with R, I'm denoting now the R transform of this object of interest, so mu to the power n, and of course the same for the G transform, so this G transform of this guy, the same for the K transform. Okay, so what kind of formulas do we get there? Good. Okay, so I erased the R transform. I still have the Cauchy transform of our original measure, but of course this is not so helpful. I need of course the R transform. I have erased it, but of course I just avoid it. And then to go over to the n-fold convolution power, we just multiply this with n. As before, we multiply it with 2. Yeah, so then we have the R transform, this guy. This is now n times the R transform of our measure mu. And mu is of course still this symmetric value. Okay, the R transform of R mu, so this was 1 plus 4 z squared minus 1 divided by 2z, which we got from solving the relation between R transform and Cauchy transform for this, and now we just multiply this with n. Good. And so we have the R transform of our free convolution measure, and now I just have to calculate the Cauchy transform again by taking Cauchy transform as the inverse of this R transform plus 1 over z. Okay, so what I get here is I have this 1 plus 4 g of z squared square root divided by 2 times g of z. That's the term, the square root term, because we have to multiply by n. And then I have minus n divided by 2z, and I'm adding the 1 over z. Subtract. No adding. Okay, so I also get minus the 1 over g of z. That's the argument. And I have the n over 2, so that's this here, minus n over 2. And then I also have to add this term, 1 over z, or 1 over the argument. Minus minus is plus. Okay, so I just have written this down. And again, you see this is still a quadratic equation in G. Okay, so which we still can solve, and the solution is the following. I'm not going to step, but I'm just giving you the solution. And again, of course, a quadratic equation has 2 solutions, but of course we choose the right one, which has the right behavior at infinity. It must behave like 1 over z. So what we get is g of z is equal to n times the square root of z squared minus 4 n minus 1 minus z times n minus 2 divided by 2 times z squared minus n squared. Good. So this is, of course, for n equal to 2, this reduces to what we had before. And for n equal to 1, it reduces, of course, to this one. But now we have it for general n, and I can now use the Stieltjes inversion formula. Again, this is something which makes sense as an analytic function for the half plane, so I can use the Stieltjes inversion formula, and I get essentially density for this. Density of mu to the n is determined as, okay, I take minus 1 over pi, and I take the imaginary part of this at the position t plus I epsilon, and then I send epsilon to 0, but again, essentially, if I'm choosing the right branch of the square root, this goes over to the real axis, so I just can replace the set here by t. So the limit goes through. So this is then n times t squared minus 4 n minus 1, square root of this, divided by 2 t squared minus n squared dt. Okay. And of course, I mean, what we get here is again a positive density for this guy. Okay, as it is clear. But maybe now you might observe maybe a strange thing, that the fact that n is here an integer is not really important for seeing that this is a probability distribution. Okay, so I mean, this also is a density if n is not necessarily an integer, but a real number, at least if it is big enough. And so what one actually observes is that this Cauchy transform here is really the Cauchy transform of a probability measure, not just for integer n's, but for all n bigger or equal to 1. Okay, this is really something strange, because this seems to indicate that this mu to the power n we do not only have for integer n, but we really can define this for non-integer powers. And this is something which in general you cannot do in a classical context. I mean, in the context of infinitely divisible measures you can do things like this, but here we have a measure which is not infinitely divisible in any sense. Also, this means in the classical case for this Bernoulli, this is just not true, but here it seems to be true, and this is a very strange thing, which is very different from the classical situation. Maybe we should have a bit closer look on this. So maybe I can first write this observation out. Also maybe we should really investigate this Cauchy transform a bit more carefully and convince yourself that this really is a Cauchy transform. If you apply Stieltjes inversion formula to it, it really gives you a probability measure for n greater or equal to 1, not just integer but real. Okay, between 1 and 2 you also might have some atoms, which, and at 2 we know there are no atoms anymore, but for n bigger than 2 there are no atoms. Between 1 and 2 you might have a density, this is a density, but there might also, this might also give you a pole which has atoms. Also you should maybe think about it. So let me just say this now. So this is, of course, first of all, clear statement is that, of course, for integer n, this is of course probability distribution, but and that's a surprising thing, however, the same is true for all n real numbers as soon as n is greater or equal to 1. So we cannot make it smaller than 1. If you could go down to 0, this would mean that you have an infinitely divisible measure. And then this would be comparable to what you have in classical probability theory. But here we are talking about a measure which is not infinitely divisible, but still it seems that you can have convolution powers with n for any real n starting at 1. case. So it seems that we can extend convolution powers mu to the power n, which of course directly only makes sense if n is a natural number, also to real powers n which are greater or equal to 1. And of course, this is something which is not true in the classical case. No? This is not true in the classical case. No? We may maybe have, let us have a look on it, and maybe also see what we are really claiming here. What does it mean to have such non-integer powers? So we are observing from this that we have something which is mu, let's say, to the power 3 over 2. So we have something, maybe let me call it mu, which is mu to the power 3 over 2. So for each n which is bigger than 1, 3 over 2, that's something. And so what does it mean? So this, I mean, we have seen those are probability measures. So we have the probability measure mu, which has the property such that if I convolve this mu twice with itself, I get the same as convolving mu 3 times with itself. So this has the property that mu to the power 3 is the same as mu to the power 2. And of course, for natural powers, we know what this means. No? This is convolving 3 times, this is convolving 2 times. No? Okay, of course, so another way, this is saying that this is this to the power 3 over 2. Okay, and so in the free world, we have something like this for this mu. But of course, classical, this is not possible. No? So classically, there's no such, there's no mu, which would have the corresponding property, namely if I take our mu to the power convolution power 3, that this is the same as mu to the convolution power 2. Because I mean the mu to the power 3 again is something which we can write down very easily. So mu is plus and minus 1, probability 1/2. So if I convolve it 3 times with itself, I get the possibilities, what I will get, minus 3, minus 1, plus 1 and plus 3. So I have minus 3. If all my 3 random variables are minus 1, we say this is probability 1 over 8. Then 2 of them can be plus 1, 1 is minus 1, which gives the sum minus 1, and I have 3 possibilities for this. So I have 3 over 8 delta minus 1, the same 3 over 8 for delta plus 1, and then I have 1/8 possibility for having all of them being plus 1, which in the sum gives plus 3. So this is the distribution of the sum of 3 times my variables, x1, x2, x3. Each of them is a Bernoulli, and they are independent. Okay. So this is the distribution of this, and this you cannot write as the twofold convolution of something with itself. Because I mean, this mu also must be discrete in the classical world, and I mean, you can check that it's not possible to have a discrete measure which gives you something like this if you convolve it twice with itself. Good. Okay. So this means in the classical world also this discreteness, because what you get here is discrete, and then it's very hard to find something like this. In the free world, I mean, this is not discrete, and then maybe it's easier to find something for other powers. Okay, but so this means here we have something which is very different from the classical world, and it turns out that actually this is now nothing special for this mu, for this Bernoulli, which is -1 plus 1, but actually this statement here is true for all probability measures, compactly supported, of course, in our context. So actually what we observed here in this example, in the existence of this semigroup of convolution powers, the existence of such a convolution semigroup, that's what we would denote by mu to the power t. Maybe it's better to use t. Maybe I write any, I think of natural numbers, but now I'm really saying that t can be any real number greater or equal to 1. So this is nothing special for a mu which we considered here, which was this Bernoulli living on plus and minus 1, but it's actually true for any mu. Okay, so I want to formulate and also prove this general statement. And of course, I mean, for any mu means at the moment for us compactly supported, because that's the only probability measures which we can deal with at the moment and for which we have the free convolution defined. Good. Okay. Statement. So that's the last statement in this chapter. Before we go over to general, not necessarily compactly supported measures. Okay, and this result is actually the side of Annika and myself from 1996. Good, so what is the statement? So we start with any compactly supported probability measure. Compactly supported okay, and then I'm insisting that we have a kind of a semigroup with respect to the additive convolution. So then there exists a semigroup. Maybe that we put the less t down there. Of course, we will also denote it by mu to the power t, but maybe let me just like this. So I have this for real t greater or equal than 1. Okay, what are those guys? The mu t's, each of them is again a compactly supported probability measure. Compactly supported probability measures are which have property that they are essentially convolution powers. And what does it mean? I mean, what does it mean? Mu to the power t. On the level of the R transform, it means that I multiply the R transform of mu just by the factor t. So that's maybe it's the easiest way to describe it. That the R transform of mu t is just the R transform of mu multiplied with t. Of course, again, for sufficiently small set. The R transform is not defined everywhere, so sufficiently small value of set. Okay, and maybe in particular, what this
means, maybe to write it more with the convolution powers, of course mu1, this is just the same as mu. So mu1 is mu. The R transform of this is just this. And then of course if I multiply the R transform with t, then of course if I have here t plus s, I multiply with t plus s and then I can split it. So this really tells me that mu of t plus s is the free convolution of mu t plus mu s. So we have mu s plus t is of course mu s plus mu t for all s and t greater than 1. Okay, and maybe we can also say that of course we have a continuity in t, and of course I mean this tells us essentially that the cumulants are continuous in t, and of course this also means that the moments are continuous. So maybe we should also write this down. So all moments or cumulants are continuous in t. And of course we write this mu sub t also as mu to the convolution power t. And of course in particular mu n, for n a natural number, of course mu n is just mu1 convolved n times into itself, but mu1 is of course mu. So it's really what we have here is mu n is really mu to the power n in the ordinary sense. But we have some interpolation for this. Good. And so let me give you the proof. And the proof uses, of course, things which we have in free probability for which we don't have a counterpart in the classical world. Because otherwise we would have the same result, similar result in the classical world, which we don't. So the proof really is not just a straightforward calculation of the R transform or so, but it really it requires something more. And what we are going to do is we also use, in a sense, multiplication of free random variables. So I'm not going to talk in this class about multiplication of free variables in general, but we're using a little bit of it, and where we will see the crucial ingredients. Okay, and so the main, so how can I see that I have those measures? Of course, the measures, saying that the R transform is t times the R transform of the measure mu is the same as saying that the free cumulants of the corresponding operator are t times the free cumulants of mu. So what I have to do is I should find some operator somewhere which has those cumulants. And of course it should be a probability measure, so I find this in the star probability space. So we have to realize, no? Now I want to go back to having operators which have this distribution. No? So I start with mu, so I know that I can realize this mu in the star probability space by some operator x. No? And from this, I have then to construct somehow an operator, let's say xt, again in the star probability space, which has this property here. No? And then I'm done. No? But of course, I have the freedom of changing my star probability space. So I just have to find somewhere in some star probability space such an operator. Good. Okay. So what we have to find, the realization of this measure mu t. So realization is this operator, a self-adjoint operator in a star probability space. So a self-adjoint operator, let's say xt in some star probability space say, such that the distribution of this xt is actually this ut. Or to put it another way, the R transform of the distribution of this xt of z is t times the R transform of the measure z. Or again, to put it another way, the cumulants of this operator xt is rt times the cumulants of this guy. And we really want to go back to cumulants to see this. So this means that the nth cumulant of xt, that's a cumulant functional, where all arguments are equal to xt, and this is t times the nth cumulant of x, x, and so on. Where x is an operator which has this distribution. Okay, and of course, I mean, when we are realizing measures in star probability spaces, we always have this, we should check that the moments are exponentially bounded. Because otherwise we don't really know whether the moments really correspond to the probability measures. But of course here we start with a compactly supported measure. So if x has the moments of this measure as its moments, then the moments of x are exponentially bounded, which means the cumulants of x are exponentially bounded. And if I then multiply the cumulants just with t, they still are exponentially bounded. So this means if I want an operator for which the cumulants are given by this, then the fact that the moments of x are exponentially bounded also mean that the moments of xt are exponentially bounded. So I really have a probability measure with compact support. Good. Okay, now, how do I get this xt? And for this xt, I use some mixture of, I use some multiplicative structure. So I'm claiming that I can get this xt by taking a kind of compression of this x with a free projection. So this is very not clear. Not clear what this means, but let me tell it. And then essentially we have to check that this guy has the right cumulants. So we claim that we can get xt by compression of x by a free projection. So this means the projection which is free from x, let's say p, and the trace of this p should be 1 over t. Because it should be relative. T must show some value. The construction must somehow depend on t. Okay, so what do I mean with this? So let us start with x. We have our mu, and this we can realize by some operator x in a star probability space. So we start from this. Start from a separate operator in, let's say, some star probability space. In the star probability space A5. Such that the distribution of this x is the given. Good. Okay, and now I have to find some other operator, this operator xt, which has this distribution ut, which has these properties. And I'm telling you that we can do this in the following way. We compress this guy here by a projection. So this means I take now a projection, which is free from this guy here, and we know that we can do free product construction. So I just can take, a projection for itself is easy to realize. The projection is something which is self-adjoint and the powers are equal to itself. So this means the distribution of this just lives on 0 and 1. So this we can realize very easily, and then we know we have free product construction, so we can assume that we have realized the x and the p in the same star probability space. And by the free product construction, which in one of the last assignments you had to inform yourself about this, then by free product constructions. Can assume that we have a projection so this means a P, which is Searcher, so P star is equal to P, and projection also means that P is equal to P star. Okay, and that this projection is on one hand free from the X, which is free from X, and on the other hand we have the freedom of prescribing the distribution of this projection. I mean, by telling what are the moments, because P squared is equal to P, I mean all powers of P are the same, so what I have to prescribe is just the first moment of P, then everything is determined. So I have the freedom of prescribing the first moment of T, and this I will prescribe as 1 over T. I mean the projection lives on 0 and 1, so the first moment can only be something between 0 and 1, and I can choose it arbitrarily. And if T is bigger than 1, 1 over T is exactly between 0 and 1. Also, I have the possibility of finding a projection which has this. But if T is getting smaller than 1, then I have problems. Because then there is no projection which has this first moment equal to 1 over T. Okay, so which is free from X. And for which I have the moments, the phi of Kn. All moments are the same, because I have a projection, so it's the same as phi of P, and this I can prescribe as 1 over T. Good, okay. And then maybe one remark which I also want to make, we can also assume that our phi, so now we have X and P in the same star probability space A phi. And I actually can also assume that phi is a trace. It's not really necessary for the following arguments, but it makes some of them easier, because I mean one also knows that free product constructions preserve a trace. Okay. And I mean phi restricted to the algebra in X is a trace, because X is commutative, and phi restricted to P is also a trace. And if I do the free product construction of this, then phi restricted to the algebra generated by X and P also is a trace. Okay, and we can assume our algebra is generated by K's, because that's the only thing we do. So I can assume that my phi is a trace. So it's a free product construction. Of course, it preserves also positivity, but it also preserves the trace. So the free product of star probability space is again a star probability space. Of course, it's important for us that we have a star probability space, because only then we give measures for Searcher random variables. So since free product preserves tertiarity property, we can assume that phi is a trace. Good. Okay, so now I have my ingredients. I have a star probability space, I have my operator X, which has the starting distribution mu, and I have projection P, which carries the information about the T, because its trace is, its first moment is 1 over T. And X and P are free. And now I should somehow give you an operator xt constructed out of these ingredients, which has the distribution mu P. Okay, so what I'm doing is actually I go now to the compressed space, so I'm not now working strictly speaking in the space A, but I'm compressing this space by looking only on elements which I get by compressing elements by P, which means multiplying to the left and the right by P. So I consider I'm changing my probability space. So now we consider a probability space which depends on T, but of course constructed from the other one. So this AT, is a subset of A, which is given by elements of the form PAP. That is from A. So this is, of course, a subset of A. So I'm just looking at elements which are of the form PAP. A is running to my original A. I'm restricting essentially to this subspace, and on this, I essentially use the old phi, but you should see that the phi is not united anymore. I mean this AT, the one from A, of course, corresponds now to P1P, which is P. So this guy has a unit, but this unit is the P. Because if you multiply guys of this form as P, then it doesn't change. Okay, so this has its unit P, and of course, in our star probability space, we need the phi of the unit to be 1. Okay, but the unit is now P, and phi of P is not 1, so we have to rescale it. So what we have to do, phi of T is now essentially phi applied to our elements, but we have to rescale it by phi of P. And then it's again united. So this means phi of T applied to an element here, which is an element of the form P of P. This is given by just taking 1 over phi of P times phi of P in P. And then of course phi T of the unit, which is P, of course is 1, because then this is phi of P and then we divide by phi of P. Good. Okay, and then it's easy to check. If A, phi was a star probability space, then this AT, the phi T, is still a star probability space. Of course, this is important. We must preserve positivity in our constructions. So, then we have this AT and phi T is still a star probability space. Unit there. In all our probability spaces must have a unit. But we have one here. This unit, so the 1 to this T is just this projection P. Okay, now I should give you an operator in this space which has the distribution mu T. And as I told you, this is now essentially the version of X in this space. So I mean, those guys are somehow compressed elements from here. Because if you think, I mean, if you have matrices and your P is a diagonal matrix, what compression means, it really means taking the corner of the original matrix and then going over to this corner. So maybe you should think a little bit about this in the language of matrix, what this really means. But this is kind of compression. For a big matrix, we are compressing it, we just take the corner out of it. Okay, good. Yeah. So we take here essentially a compressed version of our original X, and then we have to also rescale it a little bit. So here's now my proposal for this xt. So I say we should take xt as p, and here I take essentially x, but I also rescale it with t. So t is just a number. Tx is just a multiple of x. Take this, and this is an element in AT. Okay. And now I'm claiming this guy has exactly the right distribution. Okay, this is not obvious, so we have to check this. And we do this by looking on its moments. So I will now calculate its moments. And of course, I mean, moments are not so clear. We don't really know what the moments of the tree are. We know exactly what the free cumulants are. I mean, we should, at some point, we should see that the cumulants of this guy are t times the cumulants of x. But of course, we can see this if we write down the moments and then involve the moment cumulant formula. So, okay, so let us do the calculation. So, you look on this guy, and the moments, so what are the moments of this? So, I mean, of course, I'm calculating in space AT, so I should take the state phi t. So, I take xt to the power n, and of course, I go now back to the original space because there I know that p and x are free. So, I mean, all the elements which I have, p and x, are elements in the original space. So I go back and phi t is just, it's 1 over phi p, but phi p was 1 over t. So this here actually means this is t times phi p. Okay, so this phi t here is just t times the moment of xt in the original space A. Okay, and what is xt? I mean, now I'm expressing xt in terms of p and x, which are guys which I understand quite well in the space A. So I get a t here, I have the power n, so I get a t to the n. Together with this, I have a t to the n plus 1. And then I have phi, just a p x p to the power n. And so you see what I have here. I have pxp multiplied with pxp and so on. So in the middle, always a p and a p come together. I have a p squared, but p is a projection, so p squared is just p. So I have just here an alternating product of x's and p's. And I start with a p, and I end with a p. And that's where I use the triviality. I can also move one p from the beginning to the end, or the other way around, so that I really just have powers of x times p. So this here is t to the n plus 1, phi. And let's say I want to start with an x, so I have xp, xp, and so on, xp, n times. So here I have used triviality. Without triviality, I would still have a p here. But so it looks nice in this way, and I can use my more cumulative formulas more directly. But I mean, the argument would also be true if I put another p there. Good, and now I'm using, x and p are free. So how do I use this information? I am using the moment cumulative formula. So I'm FPT to the n plus 1. And then here I'm summing over all partitions. The partitions are connecting x's and p's. Okay, but x and p are free. So this means a block can only connect x's or it can only connect p's. I cannot have a block of pi which connects x and p, because mixed cumulants in free variables range, and p and x are free. So what I have here is actually, some blocks of my pi connect the x's, some blocks connect the p's. So actually I have two partitions, one for the x's, one for the p's. So I have a partition, let's say, which acts here at position 1, 3, and so on. So I put the odd positions of the x's. So 1, 3, and so on. I have a partition of the p's, which is a non-crossing partition at the even positions. But then, of course, both partitions together must also be non-crossing. The blocks of this guy are not allowed to cross with the blocks of this guy. I really have here a big non-crossing partition, and a subset of it is a non-crossing partition of x, and a subset of it is a non-crossing partition of p, but they must also be together non-crossing. So the union of them in this they must be a non-crossing partition of 2a. Okay, and what is the contribution here? I get the cumulant of the union of them, that is factorized into blocks, and then I have blocks corresponding to pi, and of course this gives me the contribution kappa pi, and there I get the cumulant of the x's. So I have here kappa pi, my x's, and the sigma gives me the cumulants of the p's. Okay, and now maybe you recognize something which you should have done in the assignment for today, namely looking on such a situation where we have essentially, we have the numbers, let's say 1, 2, 3 up to n here, and we have another copy of the numbers 1, 2 here coming alternatingly, and we are looking on non-crossing partitions which are fitting together in this way. Okay. So actually, what we are doing here is that if I'm fixing pi, of course there are possibilities for sigma which are possible. And those possibilities, there is the largest possibility, and this is exactly the Preveras complement of pi. That was something which you should put in assignments. And the sigmas, which together with the pi are still non-crossing, are exactly the sigmas which are smaller than the covariance complement. So this condition here is the same as saying that sigma is less than the covariance complement of pi. The covariance complement of pi is the biggest possible sigma, which you can have, such that they together are still non-crossing. And then if you take a smaller one, of course you still have this property. So what you are doing here is you are summing, actually, if pi is fixed, you are summing over the sigmas with this property. So what we have here is then, so we have t to the n plus 1. And then I'm summing over the pi's. I'm summing over pi and sigma, but now let me first sum over pi. Then of course this guy here only depends on pi, so I have here kappa pi of x. And then I'm summing over the sigmas, but now I'm summing over the sigmas which are smaller than the covariance complement, and for those I sum this term here. Cumulans of kappa sigma. Okay, but now if I sum cumulants over sigmas which are smaller than something, I get exactly the moment. I mean, that's the moment cumulants formula. This sum here gives me exactly the phi at this covariance complement of pi for my operator p. Okay, and so this is the moment functional applied to this. But what is this? This is a product of moments, the moment for each block. But now the moments of p are all the same. So it doesn't really matter which moment I have here. The moment is always 1 over t. Okay, and so I get here, for each block in the covariance complement, I get a factor 1 over t. So what this here is nothing else than 1 over t, the number of blocks of the covariance complement of pi. I mean, here I'm using the fact that I have a projection, so all the moments are the same. So it doesn't have to distinguish. I mean, the size of the blocks doesn't play a role. I just have to know how many blocks do I have. Each block gives the same contribution. Okay, so let's see what we have. So we have pi. I'm summing over the non-crossing partitions in pi. I'm summing cumulants of x. So this is the product of cumulants of x, product according to the block, the composition of pi. And here, this whole contribution, the sum of all the sigmas, gives me now just a factor of t. And I also have a factor of t in the beginning. So what I have here is t to the n plus 1. And then here I'm subtracting, because it's 1 over t, I'm subtracting the number of blocks in the covariance complement. Okay, and of course now it looks maybe not so nice, because here I have the covariance complement, I'm summing over pi, but then in the same assignment you also have to show that actually the number of blocks in pi plus the number of blocks in the covariance complement is always n plus 1. So this means n plus 1 minus the number of blocks in the covariance complement is just the number of blocks of pi. So this here is just t, the number of blocks of pi. And now you see that this fits very nicely with this, because here you have a product of cumulants, and you have the number of blocks, and here you have for each block you have a t. So this means you can just multiply each cumulant appearing here with a t. And this, in the end, tells you that actually the cumulants of this new guy are just t times the cumulants of the original guy. Right on the last. Here. Okay. So what I have here is now the sum over partitions and elements, and here I can take the cumulants of x, and I multiply them with t, and then I take the number of blocks. So this is now the multiplicative functions, where I'm not using the cumulants, but I'm using t times the cumulants. The point, of course, is you see, I have exactly so many factors t as I have blocks here of pi. So I can really distribute the t, 1t for each block of the pi. And this really, I mean, depends on this thing here. And of course, I mean, the Rivera's complement doesn't exist for classical partitions. So these are really arguments which have no classical element. Yeah, but then this, by the moment cumulant formula, tells me that those guys here must be the cumulants of this operator xt. I calculated the moments of xt, and I wrote it in the form which is the moment cumulant formula. And from here I can read off what are the cumulants of this guy, and you must really see. So this means cumulants of our operator xt, of course calculated in this star probability space t, phi t, they are just t times the cumulant of x. And that's exactly what I want. So I mean, the calculation is somehow, with all our combinatorial machinery, it's not very complicated, but it's still quite surprising, and it induces this fact about the Rivera's complement, that you really have a lot of structure within the lattice of non-crossing partitions. So the lattice of non-crossing partitions has much more structure than the lattice of all partitions. And this translates here into properties, relations. I mean, it's relations between multiplying free variables and adding free variables. By multiplying free variables with the free projections, we can realize a situation where actually we should be adding things. That this is related. In the classical context, this is not related at all. But here it really turns out this gives us the right thing. Yeah, that's the end of the proof. So this really shows that we have this realization of the semigroup for each t bigger than 1. Good. Okay, so this was just again an example which shows that in the free world, it's not everything is the same as in the classical world. So there are surprises to be expected. And usually you have more structure, for which there's no classical counterpart. Good, so up to now we have looked on compactly supported probability measures, and then next week, I want to show you how one can extend this to all probability measures. Again, by extending this idea that we should solve this relation between the Cauchy transform and the R transform. The Cauchy transform is defined for all probability measures, so hopefully we can use this relation also to define the R transform for all probability measures, and then define essentially the free convolution by the additivity of the R transform. Okay.